3.3, yep.
What about 3.2?
We did that last class.
And then we did 3.1 the class before.
I think we didn't have enough time to do 3.1 a week ago, so we did 3.1 and 3.2 last class, I believe.
Huh. You have our cumulative grades like set up here.
How's it going, James? Yeah, good. I have, yeah, most of the grades are back. I don't have like a summary, for like halfway through. I could maybe think about putting that together if that would be helpful.
I mean, if it don't take that much extra time,
Or why don't you, if you want, you can stop by office hours when we get back, and we can talk through.
today?
No, it'd be like when we get back from spring break.
Oh, okay. Alright, that's cool. Or I could just do the math in my head.
Yeah, you could do that.
Matter of fact, I'll use Python to do that.
Totally do that. Yeah, put in everything. Yeah, that'd be a good way to do it. All right. Happy Tuesday. How's everyone doing? I'm doing great. Have I told you I have a baby? Okay. I've used the joke too much. Welcome to class. We have a big one today. We're talking about ways of quantifying uncertainty. So, so we started part 3 thinking about how we make inferences from data, right? So we started the class thinking about data sets, working through data summarization. We spent part 1 thinking about single variables. We started working with bivariate relationships in part 2. And then we turned our attention at the beginning of class, or at the beginning of the week, last week, thinking about how we make inferences about unobservable populations, right? So, we have all this information about, what's in our data sets, but fundamentally our data set is just a realization of a random variable that we do not observe. So that's what we're turning our attention to the rest of this semester, is building statistical models to make claims about unobservable population parameters. So that's what we're turning to today. Last class, we developed the basic machinery of the central limit theorem. So we walked through this die rolling simulation. So we thought about increasingly large simulations or increasingly large samples. Each of you rolled one die, and then I collected your information. We plotted a histogram of the distribution of die rolls, which you remember was just incredibly boring. It's like, okay, like equal probability on all 6 possibilities, nothing particularly new. But then as we increased the sample size, and you told me your sample mean, this is where we started to see the distribution of sample means converge to the middle of the distribution, so the population average, the population mean. So this is what we started working with last class. What we're doing today is thinking about ways that we can actually use this in practice. There are a couple of pretty big ideas that come from the central limit theorem that we're going to use really the rest of class. So that's where we're going today, part 3.3, and then part 3.4 with hypothesis testing. We're going to do this next class. We're going to start building our first statistical models before we kick off for break. Before we get in, are there any questions? Any housekeeping I'm forgetting about? Last class we took the vote. We're pushing homework 3.4 back to after spring break. So, like I mentioned, I don't want you doing any work for me over spring break. Go catch up on sleep and all that. So we'll just do homework 3.4 when we get back from break. Also, you saw the announcement about mini-exam 3. So that'll be Thursday, the week we get back. So not right after we get back. And then we can do a review session. Any other housekeeping I'm forgetting about? Y'all doing great? All right, good to hear it. Okay, so we're going to start with where we really began this semester, right? So we started thinking about this New Jersey minimum wage study. And this was, I think this is just a great example of the kinds of things we think about, right? Like, we have this very simple prediction given to us by the simplest economic models. It's like, when we raise the minimum wage, what happens to employment? And the simplest model, of course we have many models, but the simplest one tells us that as prices go up, for whatever reason, employment should fall. So, New Jersey, like we talked about, 1992, raised the minimum wage, and then Cardin Kruger came in and surveyed a bunch of fast food restaurants to test whether the simplest theory we have holds up in reality. And so what we ended up seeing is employment actually increased by roughly 0.6 FTE. So you'll remember FTE is just full-time equivalent. It's just a way of measuring how many people are employed. And so this, we talked about how this sort of goes in the opposite direction of the main sort of simplest economic model of minimum wage. This is all a sample, right? Like Cardin Kruger go out and make one set of observations at one particular point in time. And we can make summaries of this particular sample, right? Like we can look into our data set and observe what happens on average in the sample. So like what's happening in New Jersey. But in general, the kinds of questions we're after are not about New Jersey in particular. It's something like bigger, right? It's about what happens with our models. So how do people behave, not just in this particular context. So this is, I think, a great example of the kinds of things we're turning our attention to. We're thinking about not just what's happening in our sample, but we're trying to make inference about what's happening with minimum wage sort of overall. So this is, the kind of question we're going to start asking in part 3. So like, how do we learn about the population mean if all we observe is the sample? This is the fundamental question of inference. And the sort of the building block, we're going to, the basic building block for all we do with inference rests on the central limit theorem. And like we talked about last class, the basic idea with the central limit theorem is extreme events become much less likely when you take larger samples. So you'll remember back to the die rolling example. If I roll one die, I record that observation. A 1 is just as likely as a 3 and a 4. But if I roll 2 dice, to get a 1 on average, I have to roll 2 1s, which becomes half as likely as rolling 1 1. And as I increase the sample size, the only way to get a 1 with a sample of 30 dice is if I roll 30 1s, which is just an incredibly unlikely outcome. So as we increase the sample size, the distribution of sample means moves further and further away from the extremes towards the center. So we get this sort of general movement of the sample means towards the average. And one thing we didn't really derive, but is a result of the central limit theorem, is that the distribution of sample means, as we increase the sample size, the distribution of sample means gets closer and closer to a normal distribution. And the reason this matters is because often, I mean, in general, when we look out into a population, whatever sample we're drawing, we generally do not observe the underlying population itself. Like, could you tell me the distribution of employment across fast food restaurants in New Jersey? I don't think anyone actually knows what that distribution is. All we observe are the samples that we draw from the underlying distribution. And that's a problem. Like, we want to make claims about it, but we don't actually see the distribution itself. What's powerful about the central limit theorem is that it gives us a known distribution without having to know fundamentally what the population distribution is. So like we talked about, for nearly every population distribution, we get this result. We know the general distribution of the sample means, whether they're skewed, whether they're uniform like we did with the die rolling, really whatever. And so that's the first result. We don't, we can work with distributions whether we know the underlying distribution or not. The second thing was that this sampling distribution is centered on the population. So when we're drawing samples and we're taking the mean, the distribution of these sample means is centered on the population mean. So what this tells us is that we actually can get really close to the population mean with our sample mean. And then the third thing is that the variability in sample means gets smaller as the sample size grows. So we have this, we talked about this mixed term here. It's like we get sigma from the population, and then we get n from our sample. As we increase the sample size, the variability in the sampling distribution gets smaller. Okay, any questions here? So this is what we did last class. We introduced this idea, we simulated it. We actually ran a bunch of samples and plotted the distributions, and we saw how this happened. So like as we increased the number of die rolls in each one of our samples, the distribution got closer and closer to the average of a die roll, 3.5. And it got, the distribution got tighter and tighter around that average. Okay, so what we're doing today, just to start us off, I think all of you have seen confidence intervals. How many of you have seen confidence intervals in your statistics classes? Yeah, nice. Okay, so we're going to really start here. We're going to start with these basic ideas. And we're going to not just talk about confidence intervals, but we're going to develop the intuition for fundamentally what they're doing. I think there's a lot of misconceptions around what confidence intervals tell us. So what we're going to do this class is develop the intuition using some simulations and some actual thinking through the variability to get a deeper sense about what confidence intervals are doing. Okay, so this is the set of basic ideas. When we know the population mean, which remember, knowing the population mean and population standard deviation is, in general, unrealistic. We're basically never going to know those things. But for the beginning here, we're going to assume that we do. And we're just going to work with this. We'll take these restrictions off later in class. But this is the kind of question we can ask if we were to know these kinds of things, right? Like here's our sample size. What's the probability that our sample mean, x bar, is within any number of standard errors away from the mean, right? So sort of measuring the distance between the population mean and what we're observing in our sample. These are the kinds of things we can ask. And the reason we can do this with just knowing the population parameters is we have the central limit theorem. we don't need to know the shape of the distribution as long as we know mu and sigma. And so you've probably seen a picture like this before. We can calculate the probability of drawing x bar in some region, right, like under the curve, at some distance away from mu on the horizontal axis. Right, so here we have 2 standard errors away from the population mean 0. And the way we do this is just by calculating the area under the curve between these 2 points. We've done a couple of these examples before. Y'all want to get started with another example? You like these exercises? Maybe, maybe not. Love that. So we're going to get started with a similar kind of question. So this is the question I'll ask you. Instead of thinking about 2 standard errors away from you, we're going to just ask for 1. So in this example, I'm showing you the picture of the confidence interval that contains 95% of our data, right? So if I were to draw 95, or like 1,000 observations, 95% of them would fall inside this confidence interval on average. But for exercise 3.3, I'm going to ask you for the probability that x bar is closer than 1 standard error to our mean. So, like always, we'll just hop over to the course page, click on exercise 3.3, and bring up the exercise. What's the first thing we do when we load this? Save it to your drive. So File, save a copy in Drive. All right. So there are a couple of questions here. The first one is to calculate the standard error of this sample mean. So we've talked through what the standard error represents. So the first thing to do is to set up the standard error for the sample mean. And then the second step is not to use code, is to sit down and calculate, or to construct a figure. Whether you draw this out or you think it through, to construct a figure that represents the answer to the second question. But let's start with the first one, just to calculate the standard error of the sample mean. So tell your neighbor something fun you're doing for spring break, and then sit down and construct a standard error.
I mean, what's the definition of being from work? I want to go to Alaska. I want to drive there. What about you? You want to come? Or we there? You want to come to Alaska too? We could go ice fishing.
Alaska not the question.
Alaska, bro. Don't hate on Alaska, bro. Biggest state in America. North America.
Yeah. Yeah.
I get down
For
they got universal health care.
Yeah, there hasn't been one messed up.
Like, I was looking for it, I like typed in this, and like,
Obviously, that was
oh yeah.
I was trying to figure out where the words from.
Yeah. So this one actually doesn't use any data. So it's just a bunch of questions about random variables.
Oh, okay, I see.
They wanted us to say it was questions and answer the question based off of
Yeah, exactly. Yeah, right. So it's like we have a perfectly known distribution, and the question is, what can we answer about the distribution? Yeah.
like a normal curve maybe.
I was trying to figure out for like an hour.
Maybe it's constant.
Yeah.
Yeah, that's what I was about to say.
That's what I just know last time.
Yeah. No worries.
What is this thing?
I didn't do better than this.
No, I forget to.
The standard error.
Yeah.
Yeah.
What's the difference between standard error and confidence
Well, so we use standard error to construct a confidence interval.
I remember 95%, 99% CI.
Yeah, we're gonna talk a lot about confidence intervals. Okay, someone help me out here. Someone want to tell me how to go about constructing the standard error for the sample mean using the information we have. Yeah.
It's the standard deviation divided by the square root of the sample size.
Nice. So we're just going to use the definition for the standard error, which is essentially it's the standard deviation of the sampling distribution. So it's like it depends on the sample size and the parameters of the underlying distribution. So so we could write out standard error is equal to sigma divided by np dot square root. Any questions here? And like we've talked about, like a lot of these things, the specific syntax in Python, you may forget like how to write out a square root, and that's what LLMs now are great for. So if you forgot either the definition of the standard error, or you forgot like how to use np dot square root to get a square root of the sample size, you can just use Gemini as a English to Python translator. So if you wanted to write this out, you could say the standard error. And Gemini isn't fully predictable. I'll show you a case I think later where it's going to make a mistake. And here it's even not giving the code hint. But yeah, usually that will work at least at some point. Okay, so great. Any questions about this? All right, so we all got the standard error. So the second part of the question is to construct like a visual that will help you think through the probability for the second question. So we'll take maybe a minute here. What's the probability that x falls within one standard error of mu? So we know what mu is. Let's construct a figure to answer this probability question. Is my question clear? Okay. Maybe help out your neighbor if you can. James?
Only so for the standard error is not supposed to go with the number.
Oh, yeah. So here we can just print out standard error. Yeah, nice. Yeah, thanks.
I see. I didn't do it yet, but I'm assuming maybe we just get like the lower value by subtracting sigma by the standard error, and then you get the top value, and then you get like a CDF. Okay. I didn't do that yet. Cumulative distribution function or something.
Yeah, cumulative density function.
Density function.
Ah, that's me. I remember PM. No, that's not me.
Probably, yeah, that would be probability mass function. Yeah.
No, I'm thinking of something. Yes.
No, not like that.
Okay. Does someone want to help me out? Like when you're constructing the visual to answer this question, what are you generally thinking about? So we're thinking about the area under a curve, right? So we're thinking about the probability distribution, and then we're thinking about within that probability distribution, what's the probability that we're within one standard error of the mean. So this is pretty similar to the picture we just worked with here. So we're thinking about one standard error above the mean, and then one standard error below the mean. And the classic way we solve these things is with cumulative density functions. So the way we would solve this one is we find the area under the curve up to our upper bound, and then we would subtract off, so it'd be like the whole area under the curve up to that point. But we don't want to include the area in the lower tail. So we'd find the area in the lower tail and then subtract that off to get the difference in the two CDFs. So should we just walk through this? How are y'all doing? James?
Doesn't that include 2 standardizations?
This one is for 2, yeah, and our question asks for 1, yeah. Should we do this together?
Yeah.
Okay. So the way I think about this problem, like the picture I have in my head is of the one I just showed you on screen. We have the normal distribution. We know it's normal because we're working with a sample mean. But then we're looking for one standard error in either direction around the mean. In this case, the mean is 0. So what we want is to find, we want the CDF of the upper bound. So this is, just the CDF of the upper bound. We're then going to take the CDF of the lower bound and subtract it from that upper bound. So the specific code, I have it in the slides, but that's the general idea for what the code is doing. We're going to take the CDF of the upper bound and then subtract off the CDF of the lower bound. This is pretty similar to some of the questions from the homework. So I'm just going to plug this in here. We have the standard error. We have the CDF of the upper bound. We're giving it mu plus one standard error above the average, above the mean. And then we're going to subtract off the CDF of the lower bound from the upper bound. And this is going to give us a number which represents the area between one standard error away from the average. Any questions about setting this up? Like, there are a lot of nuances in writing the code, and I think with your homework 3.1, you're getting a little more familiar with working with distributions like this. But if the specific syntax isn't feeling incredibly familiar, that's really okay. This is not a Python class. We're just using code sort of to help us think through these kinds of problems. Yeah, James.
Could you read through the code in this problem?
Yeah. So James was asking to read through this code. This first part, we have our standard error. This is just calculating the standard error like we did up here. The second part is using the stats module, which we loaded from SciPy. We're getting the normal distribution. This is a normal distribution because we're working with the sampling distribution. So it's we're in the world of the central limit theorem. We know what the distribution is. And then we're using the CDF. So this is the cumulative density function, just the area under the curve below some value, whatever we give it. And then here we're giving it the actual value. So this is like the CDF of what number? Well, we're giving it that number. This is the average, so mu, plus one standard error. So we're one standard error above the average. And then these are just telling the code the parameters for the normal distribution. So this is just where is the normal centered on? It's centered on mu. And then what's the scale? Well, it's the standard error. And then we're just going to do the same thing for the lower end here. So this is, just one standard error below the average. Okay. And then we just take the difference between those two to get the area between.
And that's still together that gives one standard error from the mean, right?
That's right. Yep. So this gives us the area that's the probability of drawing x between these two values.
So when you want to do 2 times SC.
That's right. Yeah, nice. So yeah, James is pointing out if you want 2 standard errors away from the mean, you just change this from 1 to 2. Okay, so that's a lot of writing out code. The high level ideas here, we're working with the CDF to give us the area between 2 values, which gives us the probability within our confidence interval. Whatever we've defined it, 1 standard error away from the mean, we have our probability. Does this look familiar, like from your stats class? 68%? This is the probability of 1 standard error away from the mean. This is such a common number. It's often something we memorize. But we're not going to spend a lot of time with those like stats tables because we have Python at our disposal. We can just calculate these numbers directly. Okay, any questions here? All right, so we've worked with finding probabilities between 2 values. And this is what we're calling a confidence interval. In this case, this is we talked about this as a 95% confidence interval. So 95% of our data falls within some range defined by the upper and lower bounds. But when we repeatedly draw, each time we draw an observation, separate samples fundamentally have randomness. And when we're defining a confidence interval, we're defining it as a fixed value. So it's given to us by the values of the distribution. What I've done here, just to simulate the randomness and how we think about the probabilities, like the numbers that correspond with our confidence interval. I've gone through and simulated 100 random draws. So these are 100 samples drawn from the normal distribution, the distribution we've just been working with. And I plotted them on the vertical axis. So this is the full-time equivalent we're thinking about employment at our restaurants. We're centering it on our known mean. So this is a known mean of 0 for the change in full-time equivalents. And all I've done is just plotted the random draws from the underlying distribution, the sample mean on the vertical axis. And then I've gone through and constructed a 98% confidence interval. The 98% confidence interval with these bars. And I've labeled these by color. So if our sample mean falls within our 68% confidence interval, I've colored the sample and the standard error green. And then if it falls outside the confidence interval, I've labeled it red. So you can just easily see what's the relationship between the confidence interval and the sample mean. What I've done here is shown how many samples are falling inside and falling outside the confidence interval. So when we construct the confidence interval, it's telling us a probability of something. And that something is this. Each time we draw a sample, the sample is fundamentally a different value, right? Each random draw gives us a different value coming from the underlying distribution. And that randomness shows up sort of in respect with respect to the confidence interval itself. So the confidence interval is what we've done. Let me try to say this maybe more clearly. We've constructed the confidence interval around mu. Each time we draw the sample, that sample is random. It's a different number every time we draw it. Centering the confidence interval around mu is fixed. Like the confidence interval itself is fixed. But the sample that we've drawn is random. So what this means is our sample doesn't necessarily fall within the confidence interval itself. So we've defined it, but it's fundamentally a probabilistic claim. Okay, I don't know, I hope I've communicated this clearly. What this is showing is roughly, roughly 1/3. If you look at this, it looks like roughly 1/3 of the samples are falling within the 68% confidence interval, and roughly 1/3 are falling outside. Okay, I don't know if I've communicated this very clearly, but fundamentally the idea is about the randomness, that the confidence interval is not a deterministic claim. We're making a claim about how the sample relates to the population, how close these two values are. Yeah, James.
Just to be clear, this is the confidence interval of one standard deviation of the mean.
Yes, so this is one standard deviation away from the mean, a 68% confidence interval. Yeah.
It goes like 68, 95, 99, right?
We can actually construct confidence intervals for any number we wish. This one I've just constructed to be 68. Yeah, good questions. What else? Okay, so this is all with a known population mean of 0 and a known standard deviation, right? We're assuming we know these things. What we're gonna do, I just wanna, we've done some of the math, right? And you've seen confidence intervals before. Part of what I want to communicate to you today is sort of the feeling of the randomness. So we're actually going to go through and run a simulation on using confidence intervals. You're going to tell me, we're going to construct a confidence interval. And then you're going to collect a sample, and we're going to check each of your samples against our confidence interval. And you're going to tell me whether your value falls within the confidence interval. All right. Y'all want to do another exercise? Okay. So, yeah, James.
What is sigma represent again?
Yeah, so that's the standard deviation of the population distribution. So it's the thing we'll never observe. So it's, we have, the population we're drawing from, and that it, has a distribution that generates the data. Sigma is, bless you. Sigma is just the population standard deviation. Yeah.
And then n is the sample size?
N is the sample size, right? And then mu is the mean. Yeah. All right. So what we're going to do is actually generate some samples, and then we're going to check against a confidence interval. So here I've some code to generate a sample. If you're following along in the slides, you can just copy this over. But let's see. Yeah, so we already have the sample the code to generate the sample. So here we're going to generate 331 observations, and then we're going to take a sample. So if you run this, you get a sample. And that looks like this. So we get, our sample is centered on 0. So we get both positive and negative values. The distribution is sort of exactly as you'd expect. if we were to plot this, so SNS dot hist plot and plot the sample, it's exactly as you expect. It's like, normal distribution centered on 0. If we wanted to take a mean, we could do sample.mean and get our sample mean for this specific sample. And then every time we run the sample, we get a separate number. So each one of these numbers is something different. But all centered on the same population mean. Yeah, James?
What's the code that you did when you did the SMS?
I just imported Seaborn.
Oh, okay.
I would usually put that at the top with the imports. Okay, any questions about this? Yeah, Courtney.
So you were saying the sample mean is going to be different every time because they're pulling from the same population to different samples?
Exactly. So just like every time we go out into the world and we collect our sample by collecting data, each time we collect, it's going to be slightly different. What we're doing here is just drawing a new sample every time we run it. So why is it that we're generating new data every time we run it? Yeah, so it's just the procedure that goes on. Where essentially, it's like the computer has an urn, and it's just randomly drawing different numbers every time. Okay, any questions before we start the exercise? Okay, so you have a sample. You're going to collect your sample mean using the mean. And then you're going to check whether your sample mean falls within one standard error of mu. So what we have to do is use the standard error we constructed before, and then you check it against the standard error. So one standard error above or below the mean. And what you're going to do is find a yes or no answer to this question. Does your sample mean fall within one standard error of mu? All right, so set up your confidence interval and then check your sample mean. We'll take about 2 minutes for this, and then I'm going to come around and we're going to actually collect the distribution of answers.
Wait, I thought Superman changes each time. So it's like, do we just keep the first one?
So great question. So yeah, it will change every time you rerun it. You'll just check one of them.
Okay. And then when you we could use sample.mean, and then you take that number and then you put it inside the code earlier.
So you'll just get the mean, and then you'll check it against the confidence interval.
Oh, okay. I see.
Mine was 0.22.
Yeah, we like positive numbers better. Okay. Someone want to tell me what your confidence interval is?
Question.
Yeah, James.
Do you use sample.norm because the word is samples and stats.norm still?
So I use just np random.norm for the sampling, and then I use sample.mean to get the mean. Okay, someone want to give me your confidence interval? Yeah, Ryan.
-0.5386 out of 41.
Yeah, just like either the numbers or how you constructed it.
Oh, I just did mu minus standard error, then mu plus standard error.
Nice.
And then upper and lower bound.
So Ryan's saying we're going to look at the mean and then subtract off one standard error on one side, and then we'll get the number for one standard error on the upper side. So this is mu dot standard error, or mu minus standard error, and then mu plus standard error. And if I actually just run this, I get two numbers, one for the lower end and one for the upper end. Okay, so just check your number, whether it's within the confidence interval. And then maybe just check with someone else next to you whether your number and their number are within the confidence interval. All right, you all have an answer for me? So I'm gonna walk through mine, and then you're gonna give me a yes or no answer to whether your sample mean is within this confidence interval. So for me, my number is 0.087, and that does fall within, so it's positive, so I'm just gonna check it against the upper bound for the confidence interval. And that definitely falls below 0.5. So I'm going to record this as a yes. My sample mean falls within the 68% confidence interval. So I'm going to record this as a 1. And then are we okay if I start in the front row? Okay, James? Yes. 0? Okay. 0? Okay. Yes. Okay. No. Okay. Okay. You said yes? Okay. No? Yes? 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 No? Okay. All right. Did I miss anyone? Okay, so we have all of our decisions made. So each of you has run your own sample, drawn from the population distribution with a known mu and a known sigma. We don't know the shape of that distribution, or at least in theory we don't. But we do know the shape of the sampling distribution, which is normal. That's given to us by the central limit theorem. Then what we've done is constructed a 1 sigma confidence interval around the mean, which we calculated earlier should contain roughly 68% of the observations. Each of you has a different sample, right? So you're sort of feeling the variability, right? Some of your answers don't fall within the confidence interval, and this is how we construct confidence intervals. It's part of what they mean. So let's just. Do you think this is going to be close to 68%? I think there are a lot of yeses, but let's see. So let's do np.mean class results. So this is maybe a little high. Our sample is like sort of small. If we were to repeat this 1,000 times, we'd get a number that's much closer to 68 probably. And we could simulate this with code. This is definitely not 100%. We have a lot of the observations in the room falling outside of the confidence interval. But part of what we're doing here, I want to simulate two things. One, that your individual sample is not necessarily in the confidence interval. And then second, even when we run a bunch of samples, the samples in the room are not all, on average, going to fall inside the confidence interval 68% of the time, right? Like, this number itself can fluctuate. So we're seeing some of that going on as well. Any questions about this? There's sort of randomness on those two dimensions. Okay, no questions? All right, so confidence intervals. We've gone through and generated this data. Here's the confidence interval in the slides. If we were to do this with much larger samples, many more draws from the underlying distribution, 68% of the time we constructed them in a way that they'll fall inside the confidence interval. But let me just step back a second. We've just generated lots of data from a distribution where we knew sigma and we knew mu. But when we go out into the world, we're not going to know these values. Mu and sigma are going to be unobservable to us. So we have a pretty big problem. What do we do in this case? Yeah.
Use the sample.
So what we know is the sample. We don't know the population. So how can we use this to help us make inferences about the population? Right? We've done all of this work to get us to a place where we can start thinking about making inferences about mu. But we've done all of this work using the fact that we know mu. So how do we get around this? I put this on the slides. If we knew the effect of the minimum wage, we wouldn't have to be asking these questions. So what do we do? Well, this is the one of the big ideas with what we're covering today. This is one of the foundational ideas. If we know that x bar falls within one standard deviation of mu, and mu would therefore be within one standard deviation of or one standard error of mu. If x bar is within one standard error of mu, then mu is within one standard error of x bar. To make this point as clear as I can, I've set up this figure. Do you all like these figures? No? Let me talk you through what we're looking at. This is what allows us to make claims about the population without needing to know mu. So far, what we've done is center our confidence intervals on mu. And then we checked the variability in x bar. Right? The sample mean can fall within the confidence interval, it can fall outside of the confidence interval. What we've done is center the confidence interval on mu. But because all we're interested in is the difference between mu and x bar, if we center the confidence interval on x bar instead of mu falls within the confidence interval centered on x bar in exactly the same cases that x bar falls outside of the confidence interval centered on mu. So anytime this confidence interval centered on mu contains the population, the sample mean, this confidence interval centered on the sample mean contains the population mean. Because fundamentally all we're doing is measuring the difference, the distance between x bar and mu. Any questions here? This is a pretty big idea. This is one of the foundational ideas that allows us to do inference. Any questions here? All we're doing is changing the center point of our confidence interval from being centered on mu to being centered on x bar. Yeah, James.
Does the larva include, the dots, the standard error?
Is for the first one or the?
The second one. Is it going to the bars at the standard error?
Yeah. So the confidence interval. Yeah. So in this case, it's 2 standard errors.
Yeah.
The confidence interval is centered on x bar. So we're centering the confidence interval in the second case on x bar, which is moving around. So each time we construct the confidence interval, it's going to be in a different place. Where originally we had set up the confidence interval to be centered on the known true population mean. Yeah. Yeah, good question. What else? Okay, I don't know if I've communicated this very well to you. What we're doing is moving the confidence interval from being centered on a thing we don't know to being centered on something that we do know. And now we have something to work with. We're going to start making claims using a confidence interval that's now centered on a thing we know. The one thing we're giving up by doing this is that every time we draw a new sample, the confidence interval will move. So our interpretation of the confidence interval will change slightly. But fundamentally, using this new confidence interval is not going to change how confident we are using the confidence interval. All right, so nice. Being at risk for restating the same thing 14 times, this is the main idea. We're going to center the confidence interval on the sample mean. So going back to the New Jersey example, what we're going to do is construct a 95% confidence interval using the information that Card and Kruger collected with their sample. So for Card and Kruger, they had a sample mean of 0.59 from their sample. They have one sample that they're collecting, so one observation, and one sample, 331 observations. So remember this, they're collecting one sample. And we're going to center the confidence interval on x bar. So it's x bar plus or minus 2 times the standard error. So this is a 2 sigma confidence interval, so like roughly 95%. And just plugging in the numbers here, we know the standard error to be 0.54 and the mean to be 0.59. So then we just plug in all these numbers into a computer or a calculator, and we get our confidence interval. All right, you all have seen confidence intervals before. This is the confidence interval that Card and Kruger constructed. Just to confirm we're all on the same page here. I want you to turn to your neighbor and try to answer this question. Is mu the population parameter? Is mu inside this interval? So we have a confidence interval constructed by Card and Kruger. My question for you is the population parameter inside this interval? I'm truly looking for an answer. Turn to your neighbor. Y'all like talking to your neighbors? Try to figure this out. Is mu inside the interval?
I'd say,
I would assume so. It's the aggregate.
yeah, I'm thinking there's like there's
X bar is sample.
yeah.
Yes.
How do you find the fractions? Or
Oh yeah, so that should say like percentage. So what the percentage of the class is inside, inside the interval.
how do you find the how do you do
So that's actually using the mean. Yes. Yeah, that's
So
it.
that's easy.
Yeah.
Alright. Thank you. I definitely did
Okay, someone help me out here. What do y'all think about this? Is mu inside this interval? So Card and Kruger, remember the context here. Card and Kruger went out measuring the change in employment after a minimum wage increase. And they measured, the change in employment. What they were after was whether employment moved up or down after an increase in the minimum wage. It's like a measurement of a parameter of an economic model, which is mu. Is mu inside this interval?
Yes.
So if we were to draw this many, many times, what we've done here is construct a 95% confidence interval. Let me set up a picture of what's going on. We have one draw, right? This is just one sample. It's one of these. We've drawn one sample, but we don't know which one it is. We have many draws. The specific location of our sample will never be known to us. We don't know where it is relative to the population. But what we do know is that 95% of the time, the confidence interval that we constructed will contain the true parameter, the population parameter. So it's sort of a trick question, I guess. Does that confidence interval contain the truth? Well, it turns out we're never going to know. But we do know that constructing it in the procedure that we've just walked through, it will contain the true parameter 95% of the time. But we also know every time we collect the sample, it's going to give us a different confidence interval. Every time we run the sample, the confidence interval will be different. And we can't tell whether we're in the case where our confidence interval does contain the truth or whether we're in the case that it doesn't contain the truth. That distinction will never be observable to us. But we do know the procedure to generate this confidence interval will construct a confidence interval that contains the truth 95% of the time. Okay, either does or it doesn't, and we just will not know. But we do know about the confidence interval itself. Okay, so this is so important, I bolded it and centered it on screen. If you're in the back, you might not be able to read the bottom of the screen. The confidence interval doesn't tell us about whether the value is in the interval. Our confidence is in the procedure that generates the confidence interval. The specific numbers that Card and Kruger found will change every time we construct the confidence interval. So we're not saying 95%, there's a 95% chance that the truth is on that interval. We're saying following this procedure, every time we redraw, the truth will be on the interval that we construct 95% of the time. Okay, so our confidence is in the procedure, not the numbers themselves. All right, have I communicated this clearly? I'll take that as a yes. All right, so we just walked through this whole procedure to make it possible to not need mu, right? We no longer need to think about centering the confidence interval on the population. But going through this whole procedure, we also haven't, we've still used sigma, right? We use sigma, the standard deviation of the population, to construct the standard error. So we need to do something here. This is the second to last thing we'll do today before we take off. So how do we get around this problem of not needing sigma? anyone know the idea we're about to work with? Like, if you didn't know sigma, what would you do instead?
So I'll use example mean. It's called, I don't know, it's not called composite, but some use example mean to calculate the error.
So instead of using the population, what if, as James is recommending, we use one of the sample parameters? In this case, we're actually going to use the sample standard deviation, so the variability in the sample. Let's think about how we might do this, and I'm going to show you the main problem with doing it this way, which we're then going to fix. So we're solving problems that then create other problems, but then we can fix the last problem. Okay, so we have x bar, which we're using to estimate mu. Let's try to use the sample standard deviation s to estimate sigma. So the problem with using sigma is that the problem with using s is that it itself is a random variable. So every time we observe a new sample, s itself is going to change, just like the sample mean changes. So s isn't fixed. It itself has a distribution. This is 1,000 samples with a sample size of 15. So just showing you the distribution in sample distributions. So it's like the variability of the sample. So this is how the samples are varying. The truth is here. So you can see the distribution of sample standard deviations is itself variable, which means if we replace s, just simply replace it in our calculation of standard error, we're introducing another source of variability. And because we're introducing a new source of variability, our estimates for the confidence interval are going to be less confident, right? Like, because we have this extra variability, we're not going to be quite as confident as we were before. So we have to account for this. This is we're going to make a slight digression. And if you have more interest in this digression, you can take a higher level statistics class. But this is sort of the idea. If we replace S in for sigma, we have to account for this extra variability. How many of you have seen a t distribution before? Probably almost everyone in the class. This is what it looks like. The t distribution is there specifically to account for this extra variability of doing this swap of S for sigma. So in red, I have a t distribution with a sample size of 15. And then in blue, I have a normal distribution. And then green is just somewhere in between. Because we have this extra source of variability coming from swapping the sample standard deviation for sigma, the t distribution puts more weight in the tails. So we're saying we can't be quite as confident. So we're going to make like higher probabilities in the tails. So you can see there's more red in the tails than in the normal distribution. And then we place less weight in the center of the distribution. So it's sort of more spread out and less clumped in the middle. We're sort of less confident than we were with a normal distribution. This is really all you need to know about the t distribution. And that as the sample size gets larger, it gets closer and closer to a normal distribution. So if you take the limit as n goes to infinity, the t distribution approaches a normal distribution. So in general, like, statisticians will sometimes just estimate using a normal distribution without it, like, doing this accounting, simply because they're very close to each other. But we're going to keep it realistic. Behind the scenes, the computer code is actually running a t distribution and not a normal distribution. So I wanted you to see this. Any questions about this? All right, we doing good? This is the t-distribution. This is the thing we use to perform our tests. And let's just step back and think about what we're doing in total. Like, we've gone through this whole sequence. We've thought about randomness, we've thought about distributions, and we've thought about confidence. What is it that we're doing? Well, we're trying to make a claim about the closeness of our sample mean to the population mean. We can't see the population mean. We can't even see the distribution of the population or its variability. We see nothing about the population except for the sample that we draw. But we can center the sampling distribution on x bar. So we do observe x bar, and we do know from the central limit theorem what the sampling distribution looks like. It's just normal, centered on the truth. But doing the center point shift, we can center it on the sample mean x bar. The other thing is we could swap S in for sigma. Doing that introduced a new source of variability that we have to account for with the t-distribution. But we can use the sample standard error using S. So instead of using sigma, we're just going to divide S by the square root of n to get our standard error. And then we have the shape of the distribution to be t. So it's sort of like an additional layer on top of the central limit theorem. We're not in a normal distribution, we're in a slightly modified version, what we call the t-distribution, because we have to account for this additional source of variability coming from the sample standard deviation. Okay, so for Card-and-Kruger, this is what it looked like. So, they just went through and did this entire procedure exactly as we've laid out, but estimating the confidence interval. And this is just one confidence interval. If they were to rerun the study, the confidence interval would be different. The confidence interval doesn't make a claim that the truth is within that interval 95% of the time. The confidence interval is constructed in a way that generates that 95% of the time, the confidence interval, not this one specifically, but the confidence interval we construct will contain the truth. But we're not making a 95% claim about this. Okay, any questions about all of this? These are big ideas. I know a lot of you have seen a lot of these ideas already, but I hope the intuition for fundamentally what's going on with the variability maybe clicks in a different way. These are the foundations for everything we're going to build from here on. We're going to build really the main workhorse model that we use in not just economics, but really like every branch of science uses basically the same model. So that's the main procedure. But sometimes we want to be even more specific. Instead of thinking about intervals, sometimes we want to make specific claims about a hypothesis. Like, what if I think the average effect of raising the minimum wage is something very specific? Often we use specific values equal to 0. So it's like, often we want to check whether a parameter is equal to 0 or not. This matters more when we think about slopes, which we're going to get to in part 4. But in this case, economic theory suggests, or the simple economic theory suggests that minimum wage should lower employment. But what if we want to check against 0 specifically? You've all seen, so what if we're asking a specific value, not just an interval? You've all seen null hypothesis. So a null hypothesis is just a claim we can make that's specific, right? We're just going to test something that we're interested in. In this case, I'm going to walk you through how we would check a null hypothesis of no effect of minimum wage. I'm going to check the time. We have 2 minutes. Do y'all want to finish here, or do you want to? Should we pick up next class? Jagger says yes. Can I just walk you through the broad strokes, and then we'll pick it up? So null hypothesis, just a claim we make. Sometimes we want to be more specific than a confidence interval. So the question we would then end up with is, how surprising is our data if our null hypothesis were true? And then we're going to make even more precise claims than just using a confidence interval. And the way we do this is by quantifying this level of surprise using what we call a p-value. All right, so I'll see you next class. Thursday, we have one more thing, and then we'll send you off into the ether for spring break. Stick around if you have questions. Remember, the part 2 project is due before break, so make sure you're working on that, and drop by if you have questions.
Thank you. Have a good day.
Yeah, you too.